Afternoon, or even a late good evening, wherever you are. This is the Game Changers seminar, where in this quarter we look at ideas and findings about the solar system, the universe, and our terrestrial environment. And today we have a talk on the age and formation of the moon by Thorsten Kleine, who just joined us. Next week, we will be looking at almost 50 years of coronal heating with Joan Smelts of the University Space Research Association in the United States. If you want to stay a priest of the seminar and other ISI activities, consider subscribing to our newsletter. You can do that at any part of the bottom of the ISI web pages. Our speaker today, Thorsten Kleine, is a professor of experimental and analytical planetology at the Westfälische Wilhelms-Universität in Münster, Germany. He's a member of the North Rhine-Westphalian Academy of Sciences, Humanities and Arts, a fellow of the Meteorological Society, recipient of the Clark Award of the Geochemical Society, of the Victor Moritz Goldschmidt Award and the Paul Ramdor Prize of the German Meteorological Society, and of the Nier Prize of the Meteorological Society. Thorsten specializes in isotopic studies of meteorites, lunar, Martian, and terrestrial rocks, and his work is highly cited, and he is supported by an ERC Consolidator grant. I'm very thankful to have him here today and explain how the moon, well, the Earth-Moon system formed. For the question and answer after the talk, we invite you to use the chat channel, in which case I will read the question to Thorsten, or you raise your hand and you speak for yourself. So, Thorsten, the floor is yours.
Yeah, Tillman, thank you very much for the invitation and for the nice introduction, and welcome everybody. I hope you can hear me well. If not, or if anything else is unclear, please feel free to interrupt me at any time. So as you see from the title, I want to talk about the age and formation of the moon. And the talk will mainly have these two topics, namely the formation of the moon and the age of the moon. And of course, when we talk about the formation of the moon, we will do this within the context of the giant impact model. And I want to briefly review what this model is, and then also want to show what the current problems with this model are. So perhaps a one-sentence summary: the giant impact model states that the moon formed by reaccretion of hot debris from a giant collision between proto-Earth and another large body. And this model, the basic steps in these models are depicted here in this picture taken from Stevenson in 2008. What I want to do in this talk is I want to talk about what is called the lunar isotopic crisis and how this has led to a new type of giant impact models. And in the second part of the talk, I want to talk about the age of the moon and how we can determine the age of the moon by determining the timescale of the lunar magma ocean. And towards the end of the talk, I briefly want to talk about a chronological link between formation of the moon and the end of Earth's accretion. And this actually is indicated in this picture here. In the second panel, you see that the giant impact is thought to have induced the last event of core formation on Earth. And at the end of the talk, I want to see if we can really see this in the chronology, in the age we determine for the formation of the moon and for the end of Earth's core formation or Earth's accretion. But before I get into these topics, I briefly want to give a very brief historical overview of how the giant impact model developed. And as one example, I want to give a previous model, which is called, which collectively are called the pre-Apollo models. So those models that have been popular before the Apollo missions. And one example of these models here is the fission model, in which the moon is thought to have formed by fission from a rapidly rotating proto-Earth. And this model at some point has been rejected, mainly because Earth had to have an about 4 times higher angular momentum as it has today. And the problem back then was that at the time, there was no explanation for how this extra angular momentum would have been removed. And ironically, we will see later on that in some new modifications of the giant impact models, in fact, these models work with a very high angular momentum, and by now there is a process known by which this angular momentum has been removed after formation of the moon. That is not to say that the fission model is realistic or is a way to form the moon, but it nicely shows how this giant impact model or other lunar formation models evolved over time. But now to the giant impact model. This model initially has been called the collisional ejection model. And it has been developed in the mid-70s of the last century, and perhaps motivated by the realization that the collisional growth of the terrestrial planets naturally leads to late collisions with a large body. And this model accounts for two of the key characteristics of the moon, and these are the iron depletion of the moon, because in this model, the moon mainly accretes from mantle material, which naturally explains the low iron content of the bulk moon. And it also can account for the angular momentum of the Earth and moon, if we assume a mass-sized impactor. Of course, this model has taken some time before it became accepted, and what you can read in the literature that with the 1984 conference on the origin of the moon on Kona in Hawaii, this model became widely accepted. And this picture here to the right is from a book, basically, that resulted from this conference, from an overview chapter by John Wood. And it shows it's basically one schematic of how this, one of the first schematics of how this giant impact may have occurred. Soon thereafter, or soon after this conference and this publication, there were the first numerical simulations of the giant impact. And this here are two examples of these two first papers by Willy Benz in 1986 and 1987. And these simulations made two very different very important observations. And the first observation is in the first paper that the collision of a mass-sized object with a proto-Earth generates a disk that contains sufficient mass to explain the mass of the moon. And in the second paper, what has been shown is that the collision of a differentiated impactor, so an impactor that is differentiated in mantle and core, really mainly results in the ejection of mantle material, explaining or basically predicting that the moon would form from mantle material and explaining its iron deficiency. Over time, of course, these impact simulations have improved a lot, and this here is a more recent or results of a more recent simulation from the paper by Robin Canup in 2004. And the importance is that, or what these simulations very nicely show, is that the collision with a mass-sized impactor can reproduce the observable physical characteristics of the moon. And these are a disk of approximately lunar mass, an angular momentum consistent with the present-day value of the Earth and the moon, and an iron-depleted composition and low density of the moon. So, of course, with this success of the giant impact model, you would think it's basically a solved problem because you can reproduce the observable characteristics of the moon. But there is, of course, one problem, and this problem comes from the analysis of lunar samples. Because this analysis reveals that there is a fundamental process in the formation of the moon that we do not understand. And what that fundamental process is and how the lunar samples reveal this problem will be a main topic of this talk today. So to briefly summarize this in a nutshell, so to say, the numerical simulations predict that the moon predominantly consists of mantle material from the impactor. And this impactor is often called Theia. This comes from the Greek mythology, because Theia is the mother of Selene, which is the goddess of the moon. Because the simulations predict that the moon predominantly consists of mantle material from Theia, from the impactor, we would expect to see an isotopic signature of this body in the moon. But the problem is that no such signature has yet been identified, and instead, Earth and moon are isotopically identical. And why this is a problem and what type of isotope signatures we are talking about, I want to show you now. So I'll give a brief overview or some background information about isotope anomalies. So these isotope anomalies, or those isotope anomalies which will be relevant for this talk, are isotope variations that deviate from mass-dependent fractionation. And at least for meteorites and planetary bodies, these isotope anomalies result from the heterogeneous distribution of isotopically anomalous material in the accretion disk. And this material is isotope or can be isotopically anomalous for different reasons. It can be because it's pre-solar matter, like, for instance, pre-solar grains that have been identified in the matrix of primitive meteorites. And in this case, we talk about nucleus, or we speak from of nucleosynthetic anomalies, like, for instance, anomalies in 54 chromium. But the isotopic compositions can also be anomalous because of photochemical processes in the disk or in the sun's parental molecular cloud. And this is the case for oxygen isotopes, and we will also look at this example. But bottom line is, and what is really important for the purpose of this talk, is that planetary bodies that formed at different locations of the disk likely had distinct isotopic compositions. And we will look at this in some more detail and start with the example of oxygen isotopes. This here is an oxygen 3 isotope plot. So it plots the delta 17O value against the delta 18O. And the definition of delta 17O and delta 18O is given below the figure. It is the parts per 1,000 deviation of the 17 to 16O or 18O to 16O ratio of a sample relative to that of a standard. And what you see in this diagram is samples plotting along a fractionation line. And the slope of this fractionation line is it's roughly 0.5. So this is a mass-dependent fractionation line. However, there are also samples that deviate from this terrestrial fractionation line. And this is shown with this pink diamond here. And these samples have an oxygen isotope anomaly. So this is an isotope variation that is not, cannot be explained by mass-dependent fractionation. And the size of this anomaly is given by this capital delta 17O value, which is the deviation of a sample from the terrestrial mass fractionation line. So if we now look at actual data for meteorites, we see that meteorites have very different oxygen isotopic compositions, and most importantly is that they do not follow a mass-dependent fractionation line. So they deviate from this red line, which is the terrestrial fractionation line. So all these samples are characterized by oxygen isotope anomalies, so by different delta 17O values. So with this knowledge, the question now is there an oxygen isotopic difference between Earth and the Moon? So remember, we know, or we think we know from the numerical simulations, that most of the Moon comes from the impactor. And if different planetary bodies have different isotopic compositions, we would expect to see an oxygen isotopic difference between the Moon and the Earth. And this here shows the oxygen isotopic composition of the Moon in comparison to the terrestrial composition, and also in comparison to the composition of Martian meteorites. This is now a slightly different type of plot. The y-axis, the vertical axis, has been replaced and is now directly showing the big delta 17O value. So the oxygen isotope anomaly, the deviation from the terrestrial mass fractionation line. And what you immediately see is that all Martian meteorites, shown with these black symbols, they have an oxygen isotope anomaly relative to the Earth. The Earth, the terrestrial mass fractionation line, in this case, by definition, is the horizontal line at 0. But the lunar samples, and especially the Apollo samples shown with the red symbols, they all plot on the terrestrial mass fractionation line. So what we see is that the oxygen isotopic composition of the Moon and the Earth's mantle is identical. So against our expectation, there is no oxygen isotope signature of the impactor in the Moon. And the question is, do we really expect to see one? And this is a question that has been quantitatively been assessed by Palavan and Stevenson in 2007. And the right figure here is taken from this paper. It shows the expected oxygen isotopic composition for potential impactors that collided with the Earth to form the Moon. And these compositions are shown with these blue bars here. And the way these compositions have been calculated is that these authors took accretion simulations from Chambers et al., and this is shown to the left, or in the left figure here, which basically shows successful simulations of terrestrial planet formation where 3 or 4 terrestrial planets are being produced. And what is also shown is the compositional gradient in the disk, an assumed gradient in the disk with this colored bar, and how or from where basically the different planetary bodies obtained the material they grew from. So you see, if you assume this gradient in composition, then the different terrestrial planets should have different compositions. And this is the basis for saying that we would expect an oxygen isotopic difference between different objects. Now, what they also did, these authors, they assumed the oxygen isotopic difference between Mars and the Earth to reflect a linear gradient in composition with distance from the sun. And with these assumptions, they calculated that we would expect the impactors that made the moon to have an oxygen isotopic anomaly relative to the terrestrial composition, as shown here on the right figure. So you see that none of these compositions would be consistent with the lunar compositions, which all would be to the left of this vertical dashed line. So the conclusion of this study is that the oxygen isotope results are inconsistent with the giant impact model because they do not, because the moon does not show an oxygen isotope anomaly, but it should if it mainly consists of impactor material. So Pallavan and Stevenson then proposed the solution to this problem, and this is that after the giant impact, there had been oxygen isotope equilibration between the Earth and the moon. And the idea here is that after the giant impact, the Earth is surrounded by a magma disk, and the moon then later forms out by accretion out of this magma disk. And the idea is that the terrestrial magma ocean and this magma disk is connected via a shared silicate vapor atmosphere, and that there is oxygen isotope equilibration via this shared atmosphere. This has been quantified in this study, and basically it has been shown that oxygen isotope equilibration is possible this way. As a result of this, of course, there is no chance to find an impactor signature using oxygen isotopes in the moon because it has been equilibrated later on. This process, however, obviously only works for volatile elements that can be readily equilibrated via an atmosphere. So the question is, do we see an isotopic signature for more refractory elements in the moon? And this can be assessed using different types of anomalies, which are called nucleosynthetic isotope anomalies, as I mentioned earlier. And these anomalies arise through the heterogeneous distribution of pre-solar matter in the accretion disk. And this here shows a plot of 50 titanium against 54 chromium, two elements that show very pronounced nucleosynthetic isotope anomalies among meteorites. Epsilon here means parts per 10,000 deviation of an isotope ratio from the terrestrial standard. What you can see in this plot is that meteorites fall into two distinct clusters, and these clusters have been called the non-carbonaceous and carbonaceous meteorites, shown in blue and in red. So in blue, the carbonaceous meteorites, and in red, the non-carbonaceous meteorites. And also shown is the composition of Earth, Moon, and Mars with these green symbols. You see they fall, both objects, all three objects are plotted within the NC field. This is not surprising because the non-carbonaceous meteorites, they are thought to represent the inner disk, so basically also the terrestrial planet region. Now zooming into this diagram a bit so that we can better see the composition of Earth and Moon. And as you can see, the upper two green squares are the compositions of Earth and Moon, and you see that they have identical chromium and titanium isotopic compositions. And this composition is distinct from all meteorite compositions and also distinct from the composition from Mars. So basically the story is the same as for oxygen, but the problem now is that while we can explain the oxygen isotopic similarity by this equilibration process via a shared atmosphere, we cannot do this for chromium or titanium because these elements would not equilibrate via an atmosphere. And this then has been termed the lunar isotopic crisis. I think it has been J. Milosh who first used this term, and I briefly want to summarize what this is. As I said several times, models predict that the moon consists largely of impactor material, and planetary bodies like meteorites and Mars, they are characterized by distinct isotopic compositions, and we have seen this for oxygen, chromium, and titanium. And for this reason, we expect to see an isotopic signature of the impactor in the moon. But what we find always is that Earth and Moon are isotopically identical. And as I said, the identical oxygen isotope composition, they may reflect equilibration via a shared atmosphere, but this is unlikely for chromium and titanium. So these observations, this lunar isotopic crisis, then has led to the development of a new class of giant impact models. And all of these models, the focus was, or the objective basically, to find a way dynamically to make the moon mostly out of proto-Earth mantle material. And in 2012, there had been 3 papers basically published. that presented different ways of how to do this. And it starts with Reufer et al. Published in Icarus, and they used a hit and run collision and showed that in this case, the moon mostly consists of proto-Earth mantle material. And then there were two papers published in Science, the first one by Cook and Stewart. And this actually is wrong. Cook and Stewart would be a small impactor in a fast spinning proto-Earth, and Canup in 2012 would be the collisions of two half-Earths. Sorry for this confusion. And then more recently, Hosono et al. In 2019, they argued that the moon basically formed from the terrestrial magma ocean. And in this case, even in a canonical giant impact scenario, the moon would mostly consist of terrestrial mantle material. So what all these four models have in common, that they increase the fraction of proto-Earth mantle material in the moon, in some cases even make the moon mostly out of proto-Earth mantle material. And this clearly has been motivated by this lunar isotopic crisis, by the observation that Earth and moon are isotopically so similar. And I now want to look at two of these models in some more detail. And I want to start with the small impactor model, small impactor and fast spinning proto-Earth from Cook and Stewart, published in Science 2012. And what is shown on this figure here is the provenance of the material that finally makes the moon in this collision. And these are the green dots. So all the green dots basically is the material that will finally make the moon. And I hope you can see this in this figure. But you see that most of the green dots are in the proto-Earth. So in this model, most of the material that makes the moon ultimately comes from the proto-Earth or from proto-Earth mantle. This model also, because it works with a fast spinning proto-Earth, the angular momentum of the Earth-Moon system is too high. And in this model, this excess angular momentum is removed by a so-called evection resonance with the sun, so between Earth, Moon, and the sun. And perhaps the other extreme is the collision of two half-Earths, so much larger, a much larger impact, or basically two equally sized bodies. Again, the same color coding, so all the green dots is the material that ends up in the moon, and you can see that the relation between the two bodies is about that the material that makes the moon comes in similar proportions from these two bodies. Again, this model would produce excess angular momentum, and again, it's argued that this excess angular momentum has been removed by an evection resonance with the sun. So if you now compare these new to the old models or old giant impact models, what we see is that it's dynamically possible to produce a moon mostly from Earth's mantle material. But what we also see is that it's in most cases requires very special impact conditions, and in some cases subsequent removal of excess angular momentum. So overall, the canonical model seems to be the more generic outcome of a collision. But as we have seen, this canonical model is difficult to reconcile with the Earth-Moon isotopic similarity. So after this, basically, it has been realized that perhaps we had been on the completely wrong track, and perhaps the isotopic data not at all mean that the moon mostly consists of proto-Earth mantle material, simply because perhaps proto-Earth and Theia, the impactor, were isotopically similar because they formed in the same region of the accretion disk. So it's interesting to note that this idea has been proposed several times, even probably very early on when the giant impact model has been developed, and also later on with the oxygen isotope analysis. And most recently, I think, by Nicolas Dauphin in his 2014 paper. And this right figure here is taken from this from this paper. So what is the idea here? The idea is simply that what if the accretion disk was isotopically homogeneous inside of 1.5 AU, so that all bodies formed inside of 1.5 AU had the same isotopic composition. And if then the giant impactor Theia would also have formed within this region, it simply had the same isotopic composition than the Earth's mantle, or than the Earth, and therefore we do not see any, or cannot see any, isotopic signature of the impactor in the moon. This is very different from the traditional assumption, which has been made previously. And just for comparison, the left figure here is again the results of the planetary accretion simulations from Chambers et al., showing that the terrestrial planets incorporated different proportions of material from different heliocentric distances. And if there is a gradient in compositions, we would expect isotopic difference between the Earth and the impactor. So the difference really is that perhaps, or if one assumes that there has not been this gradient up until about 1.5 AU, then perhaps Earth and impactor simply had the same isotopic composition, and therefore there is no isotopic signature of the impactor in the moon. So it seems that formation of proto-Earth and Theia in the same nebular region is an easy solution of the isotopic crisis. If that would be the case, this would be the end of this talk. But of course, it's not the case, because there is another problem coming from another isotopic system. And this is what I want to talk about now. And to some extent, this is the lunar isotopic crisis 2.0. And this problem comes from the short-lived 182 hafnium, 182 tungsten system, which is the decay of 182 hafnium with a half-life of 9 million years to 182 tungsten. So this is a very different type of isotope anomalies. It's not a nucleosynthetic isotope anomaly. It's a radiogenic isotope anomaly produced through chemical fractionation of parent and daughter elements, in this case, hafnium and tungsten, and subsequent radioactive decay. So the importance of the hafnium-tungsten system is that hafnium and tungsten have very different geochemical character or behavior. Hafnium is lithophile, a silicate-loving element, whereas tungsten is siderophile, a metal-loving element. And this then, during planetary differentiation, results in different hafnium to tungsten ratios in mantle and core. And this, if this hafnium-tungsten fractionation was early enough, then the subsequent 182 hafnium decay results in distinct 182 tungsten compositions of mantle and core material. And this is shown in this diagram on the right, which shows the epsilon tungsten values, again, time after solar system formation or CAI formation. So epsilon tungsten, again, is the parts per 10,000 deviation of the 182 tungsten a composition from the terrestrial standard value. What is shown in this diagram is the tungsten isotopic evolution over time. And the red line is representing the evolution of the chemically undifferentiated planet, so the planet before core formation took place. This evolution we know from the analysis of chondritic meteorites. So if you now assume that a body would undergo core formation at, say, 20 million years, then you would have the mantle evolving to much more radiogenic, more positive epsilon tungsten values, whereas the core basically maintains the tungsten isotopic composition it acquired at the time of core formation. This is simply because the core does not contain any hafnium. What you also see in this plot is that if core formation occurs later, say at 40 million years, then with the same hafnium tungsten ratio, you will evolve to a less radiogenic 182 tungsten composition. So what that means is that the epsilon tungsten value, or the tungsten isotope composition, is a very powerful tracer for mixing of mantle and core materials, and this is exactly what happened during formation of the moon. So why now is this important for the moon? So Theia, the impactor, likely had a very different core formation history than the Earth. We can illustrate this with two examples, for instance, by looking at the core formation timescale we determine for Mars, which is about 10 million years, whereas this timescale for the Earth is much longer, about 100 million years. So if Theia was a body with an accretion or core formation history like Mars, it would have finished forming its core much, much earlier, and therefore would have developed a very different tungsten isotopic composition in its mantle. And this is illustrated in this figure here to the right, which is taken from a recent paper by Rebecca Fischer. And it basically shows the evolution of the tungsten isotopic composition in the mantle of Earth and the impactor for two different scenarios. So the evolution of the Earth is always shown with the solid lines, whereas the impactor is shown with the dotted lines. And we're looking at two simulations. So the dark blue lines and the two lighter blue lines, they belong together. And the two black arrows here show the time of the giant impact, basically the collision of the impactor with then the proto-Earth that then results in formation of the moon. And what you can see from these calculations is at the time of the impact, the impactor Theia always had a much higher epsilon tungsten value than the Earth. So basically what we would expect as a direct consequence of the different accretion histories of impactor on proto-Earth, we would expect a 182 tungsten excess in the mantle of Theia. And therefore, we would also expect a 182 tungsten excess in the moon if the moon indeed predominantly consists of impactor mantle material. So we can look at this in some more detail, what really happens during the giant impact and why this is important for the tungsten isotopic composition. So what we are looking at really is a three-component mixture, and this is illustrated here to the left, where three components are being mixed, and these three components are proto-Earth mantle, marked with a 1, the impactor mantle, which is 2, and the impactor core, which is 3. And importantly, all these three reservoirs or components have very different 182 tungsten compositions, which reflect the core formation history in the impactor and the proto-Earth. So during the giant impact, then we mix these components, and in the Earth's mantle, we mix all three components together because most of the impactor mantle and core are simply added to the proto-Earth mantle. For the moon, however, this is very different because the moon consists mostly of mantle material, either from the impactor or the proto-Earth, and only a very small fraction of the impactor core. This small fraction is needed to account for the small lunar core, but it is a very small fraction. So it's inescapable that Earth's mantle and moon contain different proportions of mantle and core materials. And this then automatically should lead to distinct 182 tungsten compositions. So the question now is, what is the 182 tungsten composition of the moon? And is it really different from that of the Earth's mantle? And this here shows the tungsten isotopic composition now in the mu182 tungsten notation. So mu182 tungsten simply is 100 times epsilon tungsten. So it's the parts per million deviation from the terrestrial standard composition. And that notation is used because these variations are so small. And you see data for a few lunar samples shown with the blue symbols, and you see that all these samples indeed have a 182 tungsten excess relative to the composition of the present day bulk silicate Earth, which is shown with this red line in this plot. So on average, these samples given 182 tungsten excess of about 25 ppm relative to the present day bulk silicate Earth. So the question is this indeed perhaps the signature we would expect from the impactor in the moon? But there is one problem we have to consider, and this is a modification of the tungsten isotopic composition of the Earth's mantle after the impact. And this is by a process known as late accretion. Late accretion describes the addition of perhaps 0.5% of Earth's mass after the final event of core formation and after formation of the moon. And this late accretion has an effect on the 182 tungsten composition of Earth's mantle, and this is shown in this plot here, which shows the tungsten isotopic composition against the fraction of late accreted mass. So the present day bulk silicate Earth, so present day Earth's mantle, by definition plots in the lower right of this figure, so at an mu182 tungsten value of 0 and a fraction of late accreted mass of 1. And this red field here shows the effect of late accretion on the composition of the present day bulk silicate Earth. So, and if we go to the intercept with the y-axis, so basically remove all the late accretion, or the effect of late accretion, we see that we are at a mu182 tungsten value between perhaps 10 and 25 or 30 or so. So now the moon has not seen much late accretion. It has seen much less late accretion than the Earth. And so the effect of late accretion on the lunar 182 tungsten composition is much, much smaller. So the problem now is that you see, once you take this into account, then the composition of the pre-late accretion Earth's mantle is the same, or it's at least indistinguishable from the composition measured for the moon. So the excess 182 tungsten we see in the moon, this only has the effect of late accretion and probably has nothing to do with a giant impact, or is not an impactor signature. In other words, before late accretion, which means immediately after the giant impact, Earth's mantle and the moon had the same 182 tungsten composition. So you see the same story repeats again and again. No matter what type of isotope anomalies we look at, we always find that the Earth and the moon are isotopically the same. So we can look at this in a bit more, in a more quantitative way and really calculate what type of 182 tungsten composition you would expect for the moon in different types of giant impact models. And this is shown here in a plot of epsilon tungsten against the hafnium tungsten ratio of the lunar mantle. And all these red data points, these are results of a Monte-Carlo calculation of the expected 182 tungsten composition of the moon. And this is compared to the observed composition of the moon shown with this blue symbol here. And you can see that in this particular case, the observed composition of the moon plots outside of the field of predicted compositions. In this calculation, it has been assumed that the moon consists of 80% of impact or mantle material. This is where this H value of 0.8 comes from. So clearly in this scenario, we cannot reproduce the observed 182 tungsten composition of the moon just in the canonical giant impact model and by mixing of impactor and proto-Earth material. The situation is a bit better, but not really, if we assume that the moon consists only of 20% impactor mantle material and 80% are from the proto-Earth mantle. This is what this value of H equals 0.2 means. And again, you see that the observed composition of the moon somewhat plots out of the field of predicted compositions. There is some overlap, but still you see that most solutions would predict different compositions. And what you see is that in all these calculations, or in most of these calculations, what we really would expect is we would expect to see a 182 tungsten excess in the moon. So bottom line is that a simple mixing of proto-Earth and impactor material is difficult to reconcile with the Earth-Moon similarity in 182 tungsten. So this observation then has led to yet another development in the giant impact model, because the 182 tungsten results, they really seem to be only be, or it's only be possible to explain them by Earth-Moon equilibration. To say this again, this is really a different type of isotope anomaly from the nucleosynthetic isotope anomaly. So regardless of where you form the impactor, it seems that we cannot explain the 182 tungsten composition or similarity between the Earth and the moon by simple mixing between impactor and proto-Earth material. And among other things, this has motivated the development of this model here. This is from Simon Locke and Sarah Stewart. And they called this the Synestia model. And the characteristic of this model is that there has been a lot of mixing and equilibration between the Earth and the moon, or the material that later forms the moon. You immediately see from this figure that this is a very complex model. So a bottom line is that they assume a high energy, high angular momentum, a giant impact, and they postulate that this impact creates a very large structure, which they call the Synestia. And that out of this structure, the moon forms by condensation, and because it forms by condensation out of a well-mixed reservoir, there is a high chance that there had been sufficient equilibration to explain the Earth-Moon isotopic similarity. I should say, though, that it's not yet clear, at least in my understanding, as to whether the extent of mixing and equilibration is sufficient to explain the very close Earth-Moon isotopic similarity in this way. This certainly is an active area of research at the moment. So to sum this part up, I've shown to you the lunar isotopic crisis, which basically means that there is no isotopic signature of Thayer in the moon, but we would expect to see one. There are several proposed solutions, and one is that the moon predominantly formed from proto-Earth mantle material, and the other is that Thayer and proto-Earth form from isotopically similar material. I've also shown that both solutions are kind of difficult to reconcile with the Earth-Moon 182 tungsten similarity, which instead suggests that there had been extensive mixing and equilibration during and after the impact. Now, this may be possible in the Synestia model, but that remains to be tested. Okay, and with this, I want to move on to the second part of the talk, which is the age of the moon and how we can determine the age of the moon. This, in fact, is not straightforward to some extent, because the giant impact itself is not a process we can date directly. And this is because for dating, we need chemical fractionation of parent to daughter ratios. And the giant impact itself does not induce chemical fractionation of parent to daughter ratios, at least not in a predictable way. So we need another process we can use, and then use this one to infer the age of the moon. And the process that is commonly used is the crystallization of the lunar magma ocean. So that lunar magma ocean, the crystallization of this lunar magma ocean produces compositionally distinct cumulate layers. And this is illustrated to the right here in this figure, taken from a summary paper from Rick Carlson. The first cumulates that formed during crystallization of the magma ocean are olivine and pyroxene, which sank to the bottom of the magma ocean. This then was followed by the crystallization of anorthite, which floated to the top of the magma ocean, forming the anothitic crust. And then later on, Kleine pyroxene and ilmenite-bearing cumulates crystallized. And the residual magma of the magma ocean is then called creep for enrichments in potassium, rare earth elements, and phosphorus. So what is important for the purpose of this talk is that this crystallization sequence results in cumulates that have very different parent to daughter ratios of important radionuclide chronometers, such as, for instance, samarium, neodymium, and lutetium, hafnium. And this then makes it possible to date the formation of different cumulate layers during crystallization of the magma ocean, and thereby to constrain the timescale of lunar magma ocean crystallization. And this then can be linked to the formation time of the moon. And how this is being done, I want to explain in the next few slides. This approach has been used many times and by many authors. And instead of summarizing all these different attempts, I just want to give one example. And then want to show a more recent study that links this approach to a thermal and crystallization model of the magma ocean, and how this then can be used to determine the age of the moon. And the example I want to use is the model age of creep. So remember, creep is the residual liquid of the lunar magma ocean. So by determining the formation age of creep, we would determine the time at which the magma ocean has been crystallized. This figure here shows the hafnium isotopic evolution over time as determined for different creep-rich samples. Again, the hafnium isotopic data, they are shown in the epsilon notation, which again is a parts per 10,000 deviation, in this case from the chondritic evolution being representative of the evolution of the bulk undifferentiated moon. You see that creep-rich samples of different ages have been analyzed, and these have different hafnium isotopic compositions, and they plot approximately along a straight line, which basically then represents the isotopic evolution line of the creep reservoir over time. So now the intersection of this creep evolution line with the assumed bulk composition of the moon, which is the Kerr composition, which stands for chondritic uniform reservoir, which is the horizontal line at 0 in this diagram. So the intersection between these two lines then would give us the time of creep formation. And since, as I said, the formation time of creep corresponds to the formation of the residual liquid or crystallization of the residual liquid, this would then also give us the crystallization time of the magma ocean. So what is very important is that determining an age in this manner relies on one basic assumption, and this is that crystallization of the magma ocean was a single event at a well-defined point in time. And this point in time would then be this intersection between the creep isotopic evolution line and the Kerr evolution line. And with this assumption, we would obtain an age of 4.35 billion years ago. So now with this assumption, or we can compare this assumption with what we think is realistic for the thermal and crystallization history of the lunar magma ocean. And this is shown here from a recent paper by Maurice et al. Published in 2020 in Science Advances. This shows a thermal model of the magma ocean. And what it shows is the depths of the magma ocean versus time. And what you basically see in all these three cases shown here is that the depth of the magma ocean decreases over time, and this basically reflects crystallization of the magma ocean. And you see 3 different cases, and these 3 different cases have been calculated for 3 different thermal conductivities of the material of the magma ocean. The relevant one, though, is those shown with a value of 1.5, so with these dotted lines here, because this is the thermal conductivity which is appropriate for the anorthositic crust. And what you see is that the magma ocean is really long-lived. It's the crystallization time predicted by this thermal model is about 200 million years. And what that really reflects is the insulating effect of the flotation crust on top of the magma ocean. So the bad news of this is that the assumption we have just made on the previous slide of a single event of fractionation of crystallization is likely not valid. So it really implies that the model H assumption of single fractionation is not valid. But the good news is that we can use this model and this long period of magma ocean crystallization to basically combine this model with the isotopic observations to infer the age of the moon. And how this is being done, I want to show you on the next slide. So this shows the isotopic, the calculated isotopic evolution of the magma ocean. And this is done by using the thermal and crystallization model of the magma ocean combined, or use this model to calculate the isotope evolution of the magma ocean over time. And this is shown here with these gray lines. And what that can be done is to fit this calculated isotopic evolution to the observed isotopic composition and ages of the creep-rich samples. So these 4 samples shown here are exactly the same samples we have seen the 2 slides before that have been used to calculate this creep model age. So important now is that the free parameters in these calculations are the age of the moon, and this is shown with this red circle here, and the time of creep isolation shown with the blue circle. And this is basically the transition from the light gray lines to the dark gray lines. What we mean by this is creep isolation. This is the point in time when the chemical composition of the remaining magma reaches or basically matches the known composition of the creep reservoir. In doing this, all this has been done in a Monte Carlo model, and you see the resulting, or the ages we obtained from these models, you see in the lower part of this figure here, so the creep isolation time in blue and the moon formation time in red. And the age of the moon we obtain using this way, or this model, is 4.425 billion years ago, with an uncertainty of only 25 million years. And by contrast, the creep isolation time, so this may be the time of the final crystallization of the magma ocean, is much younger. It's 4.25 billion years ago. And now the question is, does this age make any sense? Or can we compare this perhaps to other age constraints we have for the formation time of the moon? And I want to show one example, and this comes from a completely different approach. And this is based basically on geochemical observations combined with accretion simulations. This is from the work of Jacobsen et al., published in 2014. And what these authors did is they observed that accretion simulations for the terrestrial planets, they reveal a correlation between time of the last giant impact and the mass of leftover planetesimals that remained in the terrestrial planet region. And they then took advantage of the fact that we know how much leftover planetesimals have been accreted to the Earth after the moon forming impact, because this is what we call late accretion, which I mentioned earlier regarding the 182 tungsten composition of the Earth's mantle. So we know from geochemical observations how much planetesimals have still been accreted by the Earth after the moon forming impact. And in this figure here, this is the gray horizontal bar. So we can simply take this estimate and use then the intersection with this correlation of time of impact and late accreted mass to infer an accretion time, or the formation time of the moon. And the age you obtain this way is 95 plus or minus 32 million years after solar system formation, or an absolute time scale 4.47 plus or minus 0.03 billion years. And as you can see, this age is in very good agreement with the age we determined from the magma, dating the crystallization of the magma ocean that I've just shown on the slides before. So there's very good agreement between these two different methods, which gives us some confidence in these ages. And the final point I want to make is that this age of the moon is in very good agreement with the uranium-lead age of the Earth, which is between 4.45 and 4.40 billion years ago. The most common interpretation of this age is that it dates the final segregation of the Earth's core. And you may remember that I mentioned earlier on that it's thought that the giant impact, the giant moon-forming impact, induced the last event of core formation on Earth. And this event basically is being dated by the uranium-lead age of the Earth, and the very good agreement between this age and the formation age of the moon inferred from the crystallization timescale of the lunar magma ocean is consistent with the idea that the moon-forming impact induced the last major core formation event on Earth. So all of this gives a very consistent picture. With this, I come to my conclusions. The giant impact model reproduces the key physical parameters of the moon. It predicts that the moon largely consists of impactor material, but so far no impactor signature has been identified in the moon. And this has been called the lunar isotopic crisis. There are several solutions, like formation of impactor in Earth and similar feeding zones, or formation of moon from proto-Earth material. Both solutions are difficult to reconcile with the 182 tungsten systematics, which rather points towards post-giant impact equilibration. The mechanism and efficiency of this equilibration, however, is still poorly understood, in my opinion. And then for the age of the moon, this can be determined by combining ages and isotopic composition of magma ocean products with thermal and crystallization models of the magma ocean. And doing it this way, we obtain a formation age of the moon of 4.425 billion years ago. And this is consistent with results from accretion simulations with geochemical estimates for the amount of late accreted mass on the Earth. And is also consistent with the uranium-lead age of the Earth, which indicates that the moon-forming impact induced the last major event of core formation on Earth. And with this, I thank you for your attention, and I'm happy to take questions.
Thank you very much, Thorsten, for this fascinating talk. Thank you very, very much indeed. There are a lot of questions. I'm sure you left us with a problem, and therefore people want to ask and discuss this. Maybe I'll just ask a first question. How much does that 182 tungsten problem depend on the assumption of significantly different core formation times for Theia and the Earth?
Not so much, actually. I would have to go back to the calculations to see what I assumed. I think I assumed between 5 and 20 million years. Mm-hmm. But I think even relaxing this may not change the result too much, because the problem really is the impactor core material. So this material will always have a very different tungsten isotopic composition, even if you form the core and the impactor rather late. And it's rich in tungsten. And the distribution of this material between the proto-Earth mantle and the moon is very different. And this automatically results in 182 tungsten differences. Although, I mean, of course, by chance, you may just produce similar compositions just by chance. It's possible, I think, but it seems to be quite unlikely, I would say.
Okay, thank you very much. So again, as in previous talks, you have two possibilities of asking questions. You can write your question in the chat, in which case I will read it to Thorsten, or you raise your hand and then Billy will give you the microphone and you can ask your question yourself. So let's start with a number of, well, a few questions from the chat. So Bill McKinnon, for instance, asked, that he's puzzled by the statement that the addition of a late veneer would lower as opposed to raise the Earth's epsilon 182. Mm-hmm.
Okay, so yeah, I should have explained this better. Chondrites, or basic, so the late veneer is on average chondritic material, and chondrites have a deficit in 182 tungsten. So in this mu notation, it would be -200. So you basically add material that is rich in tungsten and deplete it in relative terms in 182 tungsten. This is why you lower the 182 tungsten composition.
Okay. Another question, are there alternatives to the formation of the moon by impact? And there are many or several questions to that effect. For instance, Western proposed an explosion of the Earth, and there was also the question about co-accretion.
Yeah, so I'm really not an expert in the dynamics, I have to say. So I can only basically explain the difficulties of this model with explaining the isotopic similarity. A co-accretion, I think, will not work with many properties like the ion depletion in the moon. This explosion model from Wim, I cannot really judge, to be honest. So, I mean, perhaps it's time to look for other models, but at the same time, I think that the way we view terrestrial planet formation, it is, I mean, as stated in the original papers about the giant impact model, these giant impacts occurred almost certainly. So I think this is still the best model to go.
Okay, maybe go over to the raised hands. So William Ball is the first on the list. Willie, can you give the mic to William?
Hello.
Hello.
Hi. Yeah, if you have this impactor with its own distinct set of isotope ratios, and it impacts the Earth, that would change the Earth's isotopic ratios from what it was before the impact, which would mean that the Earth and Moon now have an isotopic ratio which is anomalous to what you'd expect for its distance from the Sun. So can you test that by looking at other bodies in similar orbits around the Sun?
Yeah, so I mean, if we would know the isotopic composition of Venus and Mercury, I think that would be really helpful. But the problem, of course, is that we don't have any samples from these bodies. Because much about the assumptions also of isotopic gradients and so forth that really is very hard to test because we don't have any sample from another large body than Mars. And Mars, of course, is very special. So it is not so clear if the difference between Mars and the Earth really is a gradient that also holds for the innermost solar system. So testing the idea if perhaps the inner disk was isotopically uniform would really require, I think, samples from Venus and Mercury, but this is not going to happen so soon.
Okay,
I'm afraid.
thanks.
Hans Sinecker would be next.
Can you hear me?
Yeah.
Okay, thank you very much. Thanks for a nice talk. Great overview for a layman even. So my question is, how likely or unlikely is the formation of the moon? And why does Venus not have a moon if these collisions are likely?
Well, okay. I mean, I cannot give you any numbers, obviously, but it's a fair point that, of course, it is an event by chance, perhaps an unlikely event which happened for Earth, but not for Venus. I think this is all I can say about this.
Okay.
Well,
From the chat
the reason
again.
for my question.
Sorry.
The reason for my question is that there have been speculations that the stability of the Earth and the tides and all that is important for the origin of life. So what people never consider in their estimation of the probability of life, if the moon was relevant and it's rare, it's a low probability, then they would drop the probability for life by a significant amount.
Yeah.
Okay, let's go back to the chat. Can you comment on earlier results which argued for lunar formation at 50 million years after the formation of the CAIs?
Yeah, so my question would be which earlier results?
Okay. Well, these have not been, well, maybe
Okay. Yeah, so formation, what was the number?
50 million years after CAI.
50.
50, 50, yeah.
Okay. Let me think, which one could that have been? So one problem is there had been claims of older formation ages also based on 182 tungsten, but this is problematic. There had been an earlier claim actually from myself, but that was affected by cosmic ray effects, which did not have been fully taken into account. There is a more recent claim based on 182 tungsten, but in my opinion, the problem is that there is no resolved 182 tungsten difference between the moon and the Earth once you take late accretion into account. And you also don't know if there is not a small signature from the impactor left, which would not allow you to use that system to date formation of the moon. And then there has been a study using hafnium isotopes in lunar zircons, which comes to an older age. There, I think the problem is that some cosmic ray effects may have been unresolved. This has to be redone, I think. I hope this answers the question.
Great talk, Thorsten. Why did the moon get much less late accretion than the Earth? Gravitation, focusing, or inferred from volatile deficiency?
So inferred, this is inferred from abundances of the noble metals, the highly siderophile elements, which entirely derive from late accretion. And the observation simply is that the abundance on the moon is much, much lower. The mechanism, I think, is not entirely clear. There are different processes, and that has to do with the size distribution of the impactors. So if these are large bodies, then you can explain this disproportional late accretion this way. And there also had been a study showing that the efficiency with which the impactor material is retained on the body depends on size. So the moon retains much less of the material, of the impactor material than the Earth does.
Okay, Ralph Yaumann asks, will samples from the mantle, the center of the SPA, for instance, South Polar Aitken Basin, will help to constrain the isotopic crisis?
That is a good question. I mean, there is always, of course, the issue that we may have a sampling bias because we only look at Apollo samples. Especially regarding 182 tungsten, this could be an issue that we perhaps look at not the bulk moon, but only at a specific area. So in this sense, I think this would be really helpful. On the other hand, when we look at meteorites, the story does not seem to change really. So I'm not sure, but clearly this would be helpful.
Bernard Foin asks, considering age uncertainties, plus minus 25 million years, you mentioned, the impact occurred when the Earth was 0 to 50 million years old. Do we have other constraints on the Earth age at impact?
Yeah, I think this would relate to what I've showed at the very end, that there is a good agreement with this age and the uranium-lead age of the Earth. Of course, all these ages have uncertainties, and it can go either way. But I would argue that the agreement between these two ages is quite good.
Dimitri Papanastasiou says, my recollection is that uranium, lead, Terra and Buzzerberg isotope studies get you a little past 4.5 gigayears. I think we are now close to a Gaussian knot for the age of the moon, with creep being relatively young. One best way to resolve some of the issues is to sample the South Polar Aitken Basin. Consider this a charge to the younger generation from the old guard, which will not be around for long. Okay, so that was more a comment, I think.
So does that mean that Dimitri considers me the younger generation? This is nice.
I don't know. Then there's a question to me. Please tell us how many are attending. There were 183 at the peak value. Now we have 105. Okay, and then William Wall asks, seismic waves of the Earth have found so-called large slow shear velocity provinces within the Earth's mantle. These are hypothesized to have come from Thea. How could the specific of these areas address uncertainties in the impact model?
Good question. I would have to think about this.
Okay. The oldest lunar zircons is dated at 4417 plus minus 6 million years. How can the formation age of 4425 plus minus 25 million years reconcile the zircon age?
Yeah, so I think, first of all, if you look at the age distribution, you see a very prominent peak at a later time, like 4.3. The significance of this one old zircon, or basically I think it's only one spot analysis of that zircon, is not so clear if it really is the formation age of the zircons, I would argue. And then it's still okay, I think, because the initial crystallization of the magma ocean is quite rapid. And it then slows down through the formation of the anosolitic crust. And overall, I would view this as a dynamic system where you have melting, remelting, crystallization, and so forth. So it's fine to have some older grains preserved, I think.
Okay, I think we exhausted the questions in the chat. And Thorsten, I thank you very much again for this fascinating talk.
Pleasure.
Thank you. And yeah, next week we're going to talk about, we'll have a talk about, again, a solar physics problem, and you're invited to join us then. Have a good day and a good evening wherever you are, and talk to you next week. Okay, bye-bye.